Hey everyone, I'm happy to present a paper on dynamic action inference with recurrent spiky neural networks here at the ICANN 2021. The paper is authored by Sebastian Otte, Robert Legenstein, Martin Butz and me, Manuel Traub. Sebastian Otte, Martin Butz and I are from the University of Tübingen from Germany, and Robert Legenstein is from the Graz University of Technology from Austria. And so I'd like to start with a short teaser. Here on the right you can see a so-called rocket ball flying in 3D towards a red target. And this rocket ball is a very simplistic 3D simulation with gravity and drag forces, and the ball itself has 3 rocket thrusters with which it can throttle in order to navigate around. And to make the simulation simpler, the orientation of the rocket ball is fixed and the forces from the rocket thrusters and gravity only affects its position. Also, this rocket ball is controlled by a spiky neural network, from which you can see the moving spike train here right beside the animation. And unlike a typical artificial neural network, spiky neural networks are more like a continuous simulation of more biologically plausible neurons over time. And these neurons communicate over distinct events in time called spikes, which you can see here as these dots moving over the screen. Now to the architecture, we use a so-called long short-term spiky neural network, which was proposed by Belek et al., and it is a kind of recurrent neural network, and it is composed of adaptive and non-adaptive leaky integrated fire neurons. The training of this LSNN, to which I come in a minute, can be done with a few tricks in your regular autograd framework like PyTorch, for example. In our work, we not only use backpropagation to time, but also a biologically plausible alternative based on backpropagation to time, which is called eProp. And since we directly input real values as a weighted input current into the network, and the fact that it already produces real value outputs makes the LSNN a really good drop-in replacement for your standard recurrent neural network like LSTMs, for example. And in fact, Belek et al. Showed that for many toy problems, an LSNN approaches and in some cases even surpasses the performance of classical LSTMs. And so, as I mentioned, the first kind of neurons in an LSNN are so-called leaky integrated fire neurons. And these are a simple and computationally cheap type of spiky neurons, which work here according to equation 1 and 2. And here the voltage of a neuron Vj over t is computed as a leaky integration of the weighted inputs Ij, and after a spike the neuron j is resetted by subtracting the value of the spike's threshold. And this behavior can also be seen in the graph here on the bottom, where a neuron is simulated with a constant input current, and therefore its voltage increases until it reaches the spike threshold, where it then emits a spike and the voltage gets resetted and the whole process starts again. The leaky integrated fire neuron is also very similar to the real valued output neuron of the LSNN, which is called a readout neuron. And this readout neuron is basically a leaky integrator without the reset term here in equation 1. And so now I want to briefly introduce the second kind of spiky neurons, the adaptive leaky integrated fire neurons. And these neurons now add a little bit of additional complexity in order to simulate the spike frequency adapting behavior of real biological neurons. And so observation in the mammalian brain found that some type of neurons get less and less sensitive for incoming spikes if they themselves fire more rapidly. And so here in the bottom graph you can see that the adaptive leaky integrated fire neurons simulate this behavior where the time between successive spikes increases when the neuron receives a constant input current. And this behavior is generated by increasing the base threshold for each individual neuron based here on equations 3 and 4. And here we first compute a low-pass filter of the neuron's own spike train and then add the value of this filtered spike train multiplied with the constant beta to the base threshold. And this then increases the neuron's threshold after each on spike. And so with no further activity, the neuron's threshold then decays back to the base threshold, and the key takeaway is that through these equations, an LSNN is able to preserve and backpropagate gradients over long distances back in time. And particularly the decay constant of the threshold controls how long we can backpropagate gradients before they also decay over time. And so you might now be wondering, how can we even train these spiky neurons with backpropagation through time, since the individual spikes are computed with a threshold function, and this threshold function itself is non-differentiable. So Belek et al. Here uses a clever trick by employing a pseudo-derivative in place for this non-existing derivative of the spiking function. And this pseudo-derivative, which is also plotted here in the bottom, is simply a triangular function of the voltage, and it has its maximum when the voltage exactly matches the spike threshold. And as I previously mentioned in our work, we not only train the LSNN with backpropagation, but also with a biologically more plausible alternative called eProp. And eProp, as proposed by Belek et al., is derived from backpropagation through time, and it splits the computation of the gradients into a so-called eligibility trace and a learning signal. And while this eligibility trace can be computed forward in time, the learning signal captures all remaining dependencies of the gradients on errors from the future. And to now avoid these dependencies on future error information, the learning signal can be approximated, for example, with a single backward pass. And so here we only backpropagate errors from the current time step, but not from future ones. And this then allows the complete forward computation of gradients, and it performs quite comparable to pure backpropagation through time. In order to now control the movement of the simulated rocket ball, we first train a forward model which learns to predict the next system state based on the current system state. And it also uses the current motor commands X, so here in this graph. And in our simulation, these motor commands control the throttling of the rocket's bow rocket thrusters, and the system state is simply the position of the rocket ball in 3D. And in the standard case, we train the forward model either with backpropagation through time or with eProp on randomly generated flight sequences. And once we have a trained system, we can then run it in a closed loop setting where the network is fed with its own prediction and it operates on a predefined vector of future motor commands. So here xt till xt plus n. And through this closed loop, the network envisions an imaginary future trajectory of the rocket ball based on the given motor commands. And in order to now steer the rocket ball, we can compare the predicted positions of the rocket ball with a target position and backpropagate this error back through the trained network and back through time into the inputs, which then gives us an input error. And by optimizing this input error with a gradient descent technique and repeating the cycle of closed loop and input adjustment, we can compute a vector of future motor commands that drives this imaginary rocket ball trajectory towards a desired target. And after enough optimization cycles, we can then use the first motor command xt in order to progress to the next world time step. And we then repeat the whole procedure again in order to fly the rocket ball within the simulation towards the desired goal. And instead of backpropagating through time, we can also compute the input errors within a single imaginary world time step based on an eProp variant, which also allows us to calculate the input errors forward in time. And as you can see here on the graph on the right, the different eProp variants perform very similar in terms of hovering accuracy. And only in the beginning, when approaching the target, backpropagating through time really manages to get significantly closer to the target. And in contrast to backpropagating through time, the eProp inference variants that we introduce can compute gradients forward in time. And they only need to compute one backward path through the network, but not through time. And here we use different methods which also differ in their biological plausibility. And for example, the eProp sim variant just uses the network's own weights for computing the backward path, while the EPROP SGN variant uses only the sign of the network weights for the backpropagation, and then the EPROP FB SGN variant uses random feedback weights for backpropagating errors from the readout neurons to the hidden neurons, and it then uses the sign of the input weights for propagating the error from the hidden neurons to the inputs. And this FB-SGN variant works since these random feedback weights were also used during training with EPROP. And so the readout neurons tend to align themselves with these random feedback weights during training with EPROP. And using EPROP for inference together with EPROP for training also allows us to train the rocket ball completely in an online fashion. And here we start with an untrained network, and through the EPROP-based inference, the network tries to fly towards the target and thereby generates its own experience. And using EPROP for training here allows us to perform a weight update in every dwell time step, and so over several thousand of dwell time steps, the LSNN learns a sophisticated world model, which then allows it to fly toward the given target using the EPROP inference. This, however, only works with the EPROP SIM variant, where we directly backpropagate the errors using the network own weights. And by using backpropagation time for inference, we can not only use more than one dwell time step for this closed loop inference, but we can also use a technique we call long-term planning, which enables the LSNN to plan around obstacles. And the key difference between the short-term inference, which is here visualized in red, and the long-term trajectory, here visualized in blue, is that we supply the error for the long-term inference only within the last dwell time step, and we then backpropagate it back through time through the whole imaginary flight sequence back into the inputs. And additionally, in the long-term inference, we use 6 axis-aligned distance sensors, which measure the distance to the nearest obstacle. And these are used in addition to the position as the system state. And this allows us to regularize the imagined rocket ball trajectory in order to avoid the obstacle when planning ahead. And we do this by letting the LSNN predict the future sensory inputs within this closed loop, and then using a high distance in every dwell time step as a target for these predicted sensory inputs, which then lets us regularize this imaginary trajectory in a way that the rocket ball avoids the obstacle when planning ahead. And this then allows the rocket ball to initially steer away from the target in order to navigate around this obstacle. We also tested this long-term inference in a more challenging setting, where the rocket ball, for example, can get stuck here in the corners of this T-shaped obstacle, and where also the passage around this obstacle is much narrower. And here we observed that it is obviously more challenging for the LSNN to form a valid trajectory around the obstacle, as you can see here in the left animation. But in the majority of cases, however, the LSNN manages to plan around this more complex obstacle, as you can see here in the bottom graph, where we plotted over 100 individual runs together with the median distance error here in bold over time. And so overall, we could show that short and long-term inference is not only possible with recurrent spiking neural networks, but short-term inference is also possible in a more biological plausible way. And with this, I'd like to end my talk, and thank you for your attention.